Hello everyone, welcome to The Secrets of Calculus. The previous section was on limits, which are the building blocks of everything in calculus. We are now going to focus on one area where dividing by zero is going to happen a lot, and surprising uses that come out of it. Hey, is this video too long for you? Here are the formulas. Let me know what you did with that extra free time. We're going to start by talking about Alpine Slides. These are concrete tracks that usually sneak down a mountain, and they are a lot of fun to ride. We'll just be considering Alpine Slides that don't zigzag horizontally. Now, here's the thing. This Alpine Slide here is broken. Sure, they have it in zero gravity, which is cool, but it's boring. It just goes straight down the mountain at the same speed the entire time. Secondly, the riders get a nasty jolt every time the sled starts, as it suddenly goes from not moving to moving. And the riders get thrown off the sled as it suddenly stops when it reaches the bottom. But, at least, we can calculate the slope of the slide, and hence the speed of the sled, at any given point. Okay, we need to fix this slide. The main issue is that it was built by linear equations. While the methodology is straightforward, they produce a boring and unsafe slide. So let's bring some fresh voices into the planning committee, like e to the x, x squared, sine of x, and natural log of x. They can help smooth out the bottom and top. But now, how will we know the steepness at any given point? Introducing the limit! How do we find slope? It's calculated with this formula. Now suppose that y is a function of x, and we had two x values that we wanted to work with to find the slope, a and b. We now have this formula. Now what we really want is a slope along one point, which would give us a quote-unquote tangent line. But wait, if a and b were the same point, we'd get a 0 divided by 0 situation, and the answer is literally every number in existence. What we really need is for a and b to be really, really close to each other. No problem, we can make the points scooch closer to each other with a limit. But that raises a new question. Should we make a scooch closer to b, or should we make b scooch closer to a? To make it a little less confusing, let's introduce a new constant, h, which is the x distance between a and b. We now have a new relationship. A equals b minus h, and b equals a plus h. I'd say it's easier to work with positive numbers, so I prefer swapping out b out. That would also mean that b is scooching closer to a. And now we have this slope formula. And lastly, because we're trying to construct a definition, let's replace a with x and set this equal to something. I vote we call this function f prime of x, so it's clear that some slope shenanigans happened. And actually, since this is technically a change in y over change in x, we can still call this delta y over delta x. There's just one problem: the limit. I'm becoming less comfortable with calling this delta y over delta x, because this delta part is really, really tiny. By using a limit in this way, we're allowing for convenience to take hold, and allow for h to equal 0 as soon as we use algebra to remove it from the denominator. As I described in the previous section, the limit lets us reach a threshold where math gives up and crazy stuff happens, like we'd be allowed to divide by 0. So let's make a new definition. I hereby call this dy over dx, and I hereby call it the derivative. Yes, it's a fraction, but it's also kind of notation. We'll even treat it like a variable sometimes. This d here is short for delta because the delta range has gotten so small that the name doesn't fit. Clever, right? Notation matching its purpose at its finest. And now we have the derivative function of one point that will immediately spit out the slope of a line tangent to f of x at any x we select. Here's a fun fact. Since f prime is a function, there is absolutely nothing wrong with taking the derivative again. If you started with the function f of x, here's how you would show that you like derivatives, so you took the derivative of the derivative. And of course, You could take the derivative again and again, no problem. Usually what happens if you're taking, say, the 100th derivative, you wouldn't put 100 tick marks. You'd usually see something like this. One last note, people tend not to put the y in the dy over dx when using it to say, quote, take the derivative. I will be following this pattern as well, only using the full dy over dx form when we're doing some crazy shenanigans. Now, the derivative is kind of like the child of the limit. Soon, the derivative is going to be able to do things on its own, including helping out its parent, the limit. But right now, we need to slowly but surely break away from using this limit definition. And in fact, next episode is going to be a huge mashup of a whole bunch of different shortcuts and rules and big brain ideas to find the derivative nice and quickly. Now, these shortcuts are best explained just using a ton of algebra. And it's going to be so much big braining that it's going to stop seeming like big braining. See you next episode!